Atoms almost stop moving in the deepest cold of space. This is the realm of the last cold atoms, a frontier where temperature itself could unlock the secrets of the cosmos. By the end of this journey, you will understand how the chill of the universe defines the very edge of everything we know. We will explore why a dying star's frozen ghost challenges physics, and if an eerie cold spot in the sky is a window to another reality. How far can cold take us in the search for ultimate truth? Think of a thermometer designed not for a human fever but for the cosmos itself. Its scale would be almost unimaginable, stretching from the millions of degrees inside a star's heart down to the near-perfect cold of deep space. This cosmic temperature is not a matter of comfort, it is a fundamental force. It dictates how matter behaves, how energy flows, and even how the fabric of reality itself twists and bends. Astrophysicist Dr. Elena Rodriguez explains that these temperature gradients are the engines of the universe. They drive the birth of stars within cold, collapsing gas clouds and govern the violent, heated collisions of entire galaxies. But how do you possibly measure heat in the vacuum of space, where a conventional thermometer would be useless? Scientists turn to the light itself. Every object, from a warm cup of coffee to a distant nebula, emits a unique fingerprint of radiation. By analyzing the spectrum of this light, its specific colors and intensities, researchers can read the temperature of an object millions of light years away. They also rely on quantum effects, observing how atoms behave and interact at these incredible extremes. The most profound reading from this cosmic thermometer comes from all around us, a faint whisper of radiation that fills every corner of the sky. This is the cosmic microwave background, the afterglow of the Big Bang, and it reveals a universe that has cooled to a mere 2.7 Kelvin. That is just 2.7 degrees above the absolute coldest temperature possible. This foundational chill is the baseline of the cosmos, the quiet stage upon which all other cosmic dramas play out. Understanding this deep cold is the first step toward the ultimate quest, a journey to the final frontier of temperature itself, absolute zero. Absolute zero represents a finality, a temperature so profound that atomic motion itself would simply stop. In laboratories across the world, scientists use an arsenal of lasers and magnetic fields to push atoms into a state of deep cold, reaching within a billionth of a degree of that ultimate limit. This is not merely a quest for a record. It is a journey into a new realm of physics, a place where the ordinary rules of reality dissolve. At these temperatures, a strange transformation occurs, creating what is known as a Bose-Einstein condensate. Imagine a crowd of individual atoms losing their identities, merging together to act as a single, giant superatom. This bizarre state of matter was pioneered by Nobel laureate Wolfgang Kettel, whose work reveals a universe where matter behaves more like a wave than a collection of particles. These experiments are not just academic curiosities. They offer tangible clues to understanding superconductivity, where electricity flows without resistance, and may even shed light on the mysterious nature of dark matter. Yet the final prize, absolute zero itself, remains forever out of reach. The reason lies in the quantum world itself, where a faint, irreducible energy known as quantum fluctuations ensures that atoms can never be completely still. This inherent fuzziness of reality prevents us from ever touching the true bottom of cold, but by coming infinitesimally close, we create a pocket of eerie calm that mirrors the vacuum of space itself. In these ultra-cold labs, we are essentially building a miniature cosmos, a simulation that allows us to probe conditions near the very edge of the universe. The last cold atoms, suspended in their magnetic traps, become our window into the cosmos's ultimate boundaries, a theme that leads us directly to the mysterious cold spots scattered across our own sky. Far out in the depths of space, a dying star has performed a magic trick that defies all expectation. It has created the Boomerang Nebula, a place so profoundly cold that it holds the title of the coldest known natural object in the entire universe. This beautiful bow-tie-shaped cloud of gas, located 5,000 light-years away, has a temperature of just 1 Kelvin. That is a single degree above absolute zero, and even colder than the faint background glow of the Big Bang itself. This is not the gentle chill of a winter night. This is the deep, relentless cold of the cosmic void, a natural refrigerator operating on a staggering scale. The secret to this incredible cold lies in the nebula's death throes. The central star is shedding its outer layers at a ferocious speed, expelling gas outward at over 150 kilometers per second. This is where the physics becomes truly fascinating. Astronomer Raghvendra Sahai and his team identified the mechanism as adiabatic cooling. You can experience a tiny version of this right here on Earth. When you use a spray can and feel the nozzle get cold, that is adiabatic cooling in action. The compressed gas inside expands rapidly when released, and as it expands, it does work, stealing thermal energy from its immediate surroundings and causing the temperature to plummet. The Boomerang Nebula is essentially a cosmic spray can, but on an unimaginable scale. Its vast, rapidly expanding cloud of gas is doing work on a galactic level, pulling heat away and creating a pocket of profound cold. To map this intricate structure, scientists turn to powerful instruments like the Atacama Large Millimeter Array, or ALMA. This network of radio telescopes, situated high in the Chilean desert, acts like a giant camera, capturing the faint whispers of radiation from the nebula's cold gas and dust. These observations reveal more than just a pretty shape. They show us the final breaths of a star, a process that seeds the galaxy with heavy elements forged in its core. This celestial deep freeze directly challenges our models of thermodynamics, forcing us to ask if such extreme cold spots are common cosmic occurrences. Could these natural refrigerators be essential players in the life cycle of galaxies, chilling the raw materials for future stars and planets? The existence of the Boomerang Nebula suggests that the universe has its own methods for achieving temperatures we once thought were only possible in our most advanced labs. It is a stunning reminder that the last cold atoms are not just a human creation, but a fundamental part of the cosmic story. This faint afterglow from creation itself is the cosmic microwave background. It is a wall of ancient light that has been traveling for over 13 billion years, a relic from the moment the universe became transparent. Today, it fills every cubic centimeter of space with a uniform, profound chill of just 2.7 Kelvin. Its discovery was almost accidental. In the 1960s, two radio astronomers, Arno Penzias and Robert Wilson, were troubleshooting a persistent, mysterious hiss in their antenna at Bell Labs. They pointed the horn-shaped instrument at the sky, and no matter where they looked, the static remained. They even famously cleaned out a layer of pigeon droppings, but the noise persisted. That stubborn, uniform hiss was not a technical glitch. It was the faint echo of the Big Bang, the oldest light in the universe, and it earned them a Nobel Prize. This discovery gave us our first clear snapshot of the infant cosmos, a time when it was a searing hot plasma of particles and energy. As the universe expanded and cooled, that light stretched into the microwave part of the spectrum, becoming the cold whisper we detect today. But the story does not end with a uniform glow. cosmologists like George Smoot began looking deeper, searching for tiny imperfections in this cosmic backdrop. They discovered that the cosmic microwave background is not perfectly smooth. It is imprinted with minute temperature fluctuations, tiny spots that are just millionths of a degree warmer or colder than the average. These anisotropies are the universe's genetic code. They are the seeds of all cosmic structure. The slightly denser, warmer spots had a little more gravitational pull, attracting matter from their surroundings over billions of years. These tiny ripples grew into the vast cosmic web we see today, the great walls of galaxies and the immense voids between them. The Planck Space Observatory mapped these fluctuations with stunning precision, revealing a detailed blueprint of the cosmos. Its data tells us the universe's age, its composition, and even the influence of the mysterious dark energy that drives its accelerated expansion. Yet within this map lie deeper puzzles. One of the most intriguing is the existence of a particularly large and profound cold spot, a region of space that is significantly chillier than the surrounding background. Some theorists propose this could be a statistical fluke, a cosmic coincidence. Others wonder if it is something far more extraordinary. Could this cold spot be a bruise, a relic of a collision with another universe in the vast multiverse? It is a radical idea, suggesting that our observable cosmos is just one bubble in a frothing sea of realities. This pervasive chill of the cosmic microwave background is more than a historical relic. It is the ultimate baseline temperature of the universe, the cold canvas upon which the hot drama of stars and galaxies is painted. It forces us to ask what other cold anomalies might be hiding in the darkness, waiting to reveal even deeper truths about the edge of everything. While the Boomerang Nebula and the cosmic microwave background represent nature's grand cold, scientists have brought the quest for ultimate cold back to Earth. Inside laboratories that seem more like science fiction, researchers are creating their own pockets of the cosmos. They use intricate devices to chill atoms to temperatures within a billionth of a degree of absolute zero. At these nanokelvin scales, the familiar world of solid matter dissolves into something far stranger. The primary tool for this incredible feat is laser cooling. Imagine shining a carefully tuned laser at a cloud of atoms. The photons of light, each carrying a tiny push, act like a thick, syrupy fluid that slows the atoms down. Since temperature is just a measure of atomic motion, slowing them is equivalent to making them profoundly cold, but the process does not stop there. The very fastest and therefore warmest atoms are then allowed to escape, much like a cup of coffee cools as its most energetic water molecules evaporate. This technique, called evaporative cooling, leaves behind an ultra-dense, ultra-cold cloud. In this state, atoms lose their individual identities. They begin to behave not like discrete particles, but like overlapping waves, merging into a single quantum object known as a Bose-Einstein condensate. This is the realm explored by physicists like Deborah Jin, who pushed the boundaries even further by creating the first fermionic condensate. Fermions are a different class of particles, the very building blocks of matter, and getting them to cooperate in this way was a monumental achievement. Her work opened a door to simulating some of the most extreme objects in the cosmos. These lab-made condensates can act as stand-ins for the super-dense matter inside neutron stars, or help us understand the perplexing mechanics of high-temperature superconductors. To contain these fragile clouds, scientists use devices called optical lattices. These are not physical cages, but crisscrossing patterns of laser light that create a landscape of energy hills and valleys, holding the atoms in place for study. The ultimate laboratory for this research is not on Earth at all. The International Space Station hosts the Cold Atom Lab, a facility that leverages the pristine environment of microgravity. On Earth, gravity constantly pulls the delicate condensate down, limiting observation time to mere fractions of a second. But in orbit, freed from that pull, these quantum states can persist for over 10 seconds. This allows researchers to study their wave-like properties with unparalleled precision, watching as they ripple and interfere with each other in a delicate quantum ballet. These are not just abstract experiments, they are direct probes into the fundamental nature of reality, using the last cold atoms as our guides. By creating these miniature, controlled universes, we are testing the very laws that govern the cosmos, from the behavior of dark matter to the information paradox of black holes. This brings us to a profound and unsettling question, one that connects our tiniest labs to the largest structures in existence. But there is another, deeper chill that permeates the cosmos, one we cannot see with any telescope. This is the cold grip of dark matter. This mysterious substance makes up over 80% of all the mass in the universe, yet it refuses to interact with light. We only know it is there by the ghostly pull of its gravity, a force that spins galaxies faster than they should and bends the light from distant stars. For decades, its true nature has been physics's greatest unsolved puzzle. Now, a startling idea is emerging, one that connects this invisible cosmos directly to our quest for the deepest cold. What if dark matter itself is frozen? Theorists like Dr. Lisa Randall explore the possibility that dark matter particles could be incredibly light and slow-moving, forming what is known as cold dark matter. This material is thought to clump into vast, diffuse halos that envelop galaxies like ours, their presence revealed only through subtle distortions in spacetime called gravitational lensing. But the most intriguing candidates are particles known as Axions. These hypothetical entities are so lightweight and numerous that they could collectively behave in a profoundly strange way. In the cold, quiet depths of space, Axions might naturally condense into a cosmic-scale Bose-Einstein condensate. Imagine an entire galaxy being cradled by a single, gigantic quantum wave made of invisible matter. This would explain why dark matter forms such smooth, spherical halos around galaxies, its quantum nature smoothing out any sharp edges on a cosmic scale. To hunt for these elusive particles, scientists have built some of the most sensitive experiments on Earth. One is the Axion Dark Matter Experiment, or ADMX. It operates deep underground, inside a powerful magnet and a chamber cooled to near absolute zero. This incredible cold is necessary to eliminate any thermal noise that might drown out the faint, predicted signal of an axion converting into a microwave photon. It is like trying to hear a single, specific note in a silent, frozen concert hall. The search is a monumental technical challenge, a testament to how the pursuit of the coldest temperatures is inextricably linked to uncovering the universe's biggest secret. If dark matter does possess this quantum, wave-like nature, then the ultra-cold atoms we create in our labs become more than just curiosities. They become vital analogs. By studying how our own condensates behave, we can test ideas about how a dark matter condensate might warp space-time or influence the rotation of galaxies. This chilling possibility suggests that the vacuum of space is not truly empty. It may be filled with a frigid quantum sea of dark matter, and the last cold atoms we create are our best hope for learning to navigate its hidden currents. This seemingly empty void is actually a seething ocean of energy. The vacuum of space, far from being a true nothingness, is defined by a constant, fizzing activity at the smallest scales. Quantum mechanics tells us that pairs of virtual particles and their antiparticles spontaneously blink into existence, borrowing energy from the vacuum for an immeasurably brief moment before annihilating each other. This endless dance of creation and destruction is not just a theoretical curiosity. It gives the vacuum a real, measurable energy density, and this energy is intimately linked to temperature. We can see its effects through a phenomenon predicted by physicist Hendrik Casimir. He envisioned two perfectly smooth, uncharged metal plates placed incredibly close together in a vacuum. The empty space between the plates restricts the kinds of quantum fluctuations that can occur there, while outside the plates, a wider variety of fluctuations are possible. This imbalance creates a subtle pressure, pushing the plates together with a faint but detectable force. It is as if the vibrant energy of the void itself is squeezing them. This Casimir effect has been measured in laboratories using incredibly cold atoms, which act as perfect probes for these delicate quantum forces. At the ultracold temperatures we create, where atomic motion nearly ceases, these subtle quantum effects are dramatically amplified. The chaotic jostling of heat is silenced, allowing the faint whisper of the vacuum's energy to be heard. Some physicists even speculate that these lab-based experiments are creating a microscopic analog of the very force that drives the universe apart, the mysterious dark energy. This connection suggests that the vacuum's behavior is not constant, but is defined by its temperature. A colder vacuum may behave in profoundly different ways, and by chilling atoms to their quantum ground state, we are essentially tuning the vacuum itself to see how it responds. The reality of these quantum fluctuations is so fundamental that they present a real-world challenge for our most sensitive instruments. At the LIGO Observatory, which detects gravitational waves from colliding black holes, scientists must contend with a constant, low-level noise. This noise comes from the quantum fluctuations of the vacuum within the laser beams themselves, a limit imposed by the very fabric of reality. To peer deeper into the cosmos, they are now turning to the very principles of ultra-cold physics, developing techniques to cool components and squeeze the quantum noise, pushing the limits of what we can observe. This vibrant, energetic emptiness reveals that temperature is the key that unlocks the vacuum's true nature. The last cold atoms we create are not just objects of study. They are our most delicate tools for probing this seething quantum sea, hinting that the ultimate edge of reality may be written in the language of cold. Deep within the cosmic flow, a mysterious force tugs at our entire galactic neighborhood. This is the Great Attractor, a gravitational anomaly of such immense power that it pulls entire galaxies, including our own Milky Way, toward a point in space we cannot even see. Its location lies directly behind the crowded central plane of our galaxy, in a region astronomers call the zone of avoidance. Here, thick clouds of dust and stars block our view in optical light, creating a seemingly impenetrable wall. Yet the universe has more than one way to see. To pierce this cosmic veil, scientists turn to radio telescopes, instruments that can detect the faint whispers of cold atomic hydrogen gas. This gas, chilled to just a few tens of degrees above absolute zero, emits a characteristic radio signal as its electrons change energy states. It is a beacon in the dark. Astronomer Renée Cron-Courtoueg has dedicated her career to mapping this hidden realm, using surveys from instruments like the Parkes Radio Telescope in Australia. Her work reveals vast rivers of cold hydrogen gas flowing through the zone of avoidance, tracing the outlines of previously unknown galaxies and clusters, all being drawn toward the same immense gravitational center. By charting these cold atomic streams, we are not just mapping hidden structure, we are mapping the source of the pull itself. The temperature of this gas becomes a critical clue. When researchers create detailed temperature maps of the region, they find intriguing dips, pockets of space that are noticeably colder than their surroundings. In the warmth of a typical galaxy, collisions between atoms and radiation from stars keep the gas energized. A pronounced cold spot, therefore, suggests something unusual. It could be a region where matter is surprisingly sparse and quiet, a cosmic void where little is happening to heat the interstellar medium. Yet, the gravitational pull from this same area is overwhelmingly strong. This creates a profound paradox. How can a region with such feeble, cold matter exert such a powerful gravitational force? The answer likely lies in the invisible architecture of dark matter. These cold spots may be tracing the dense cores of dark matter halos, structures that possess immense mass but emit no light and generate no heat. The cold atomic hydrogen is simply a tracer, a flotsam caught in the grip of this unseen behemoth. Its low temperature is a direct result of swimming in the cold, dark shadow of the true giant. This makes temperature a revolutionary tool for cosmology. We are learning to read the cosmos not just by its light, but by its chill. A cold shadow on a radio map is no longer just an empty patch. It is a potential signpost pointing directly to the hidden mass that shapes the motion of galaxies. The Great Attractor's cold shadow forces us to accept that the last cold atoms, whether in deep space or in our labs, are the most sensitive probes we have for the invisible forces that truly govern the universe. The startling chill of the cosmic microwave background carries a secret message from the universe's first moments. This message was written during a period of unimaginable violence called cosmic inflation. In a fleeting fraction of a second, the entire cosmos is thought to have expanded faster than the speed of light, stretching a subatomic speck into a vast, embryonic universe. Physicist Alan Guth championed this radical theory to explain the universe's remarkable uniformity, but inflation did more than just smooth everything out. It also magnified the faintest whispers of the quantum world. At these tiny scales, empty space is never truly still. It fizzes with quantum fluctuations, where pairs of virtual particles constantly pop in and out of existence. During the hyper-fast expansion of inflation, these tiny ripples in the fabric of spacetime were stretched to cosmic proportions. They became the seeds of all structure. The denser regions of these primordial ripples, packed with a little more energy, corresponded to slightly warmer spots. The less dense regions, the cosmic valleys, were the cold spots. Think of blowing up a balloon with a faint, random pattern of dots drawn on its surface. As the balloon inflates to an enormous size, those tiny dots become vast continents. In the same way, inflation took microscopic quantum ripples and blew them up to scales of billions of light-years. These imprints were then frozen into the cosmos when the hot plasma of the Big Bang finally cooled enough to release the cosmic microwave background radiation. Missions like the Wilkinson Microwave Anisotropy Probe, or WMAP, have mapped these temperature variations with exquisite detail. The colder spots in this ancient light, those regions of slightly lower density, became the great voids we see today. They are the empty stretches between the cosmic web. The warmer spots with their extra gravitational pull acted as anchors, pulling in surrounding matter over billions of years to form the first stars, galaxies, and colossal clusters. The entire architecture of our observable universe, from the largest supercluster to the most isolated void, was predetermined by this primordial pattern of hot and cold. This means the coldest atoms drifting in the vast emptiness of a cosmic void are not random. They are the direct descendants of those initial cold spots created by quantum fluctuations during inflation. They are ancient relics carrying a memory of the universe's most explosive birth pang. The last cold atoms we study in our laboratories, suspended in magnetic traps, might therefore hold a direct link to that primordial chill. By probing their quantum behavior today, we are essentially reading the same cosmic code that was written in the first fleeting instance of time. This profound connection reveals that temperature is not just a reading on a scale. It is the fundamental sculptor of reality, a force that carved the cosmos from quantum noise, guiding us toward the ultimate tools for exploring its final frontiers. That ancient whisper from the Big Bang holds a cosmic bruise. Tucked away in the constellation Eridanus lies one of the most baffling features ever mapped in the sky, the CMB cold spot. This region of the cosmic microwave background is not just slightly cooler, it is a profound chill, a vast expanse of space significantly colder than the surrounding cosmic glow. Data from the Planck satellite revealed its true scale, a colossal patch of sky nearly 1.8 billion light-years across, with a temperature anomaly so large that it defies easy explanation. This is not a minor statistical fluctuation. It is a cosmic anomaly on a grand scale, and its origin has split cosmologists into competing camps. The first and more conservative theory points to a supervoid. Imagine a universe mostly filled with the great cosmic web of galaxies, but here there is a staggering emptiness, a region where matter is unusually sparse. As light from the cosmic microwave background travels through such a void, it must climb out of this gravitational well. According to the integrated Sachs-Wolf effect, this journey saps the light's energy, causing a measurable drop in temperature, leaving a cold imprint on the map. The problem is one of scale. For a supervoid to cause the cold spot we see, it would have to be so immense and so empty that it challenges our best models of how cosmic structure forms. It would be the greatest void in the known universe, a statistical outlier that makes many scientists deeply uncomfortable. This has led to a far more radical proposal. Theoretical physicist Laura Mersini-Houghton has put forward a breathtaking idea. What if the cold spot is not a void within our universe, but the scar from a collision with another universe? In the multiverse theory, our cosmos is just one bubble in an infinite froth of realities. The cold spot in this scenario could be the imprint left when our budding universe brushed against a neighboring bubble of spacetime. The energy drained away in that primordial contact, leaving behind a permanent cold shadow. It is a staggering concept, suggesting that the coldest spot on our cosmic map is a window to another reality entirely. The debate between the supervoid and the multiverse collision theory is far from settled. Each explanation pushes the boundaries of physics in its own way. One requires a void of improbable size, the other, evidence for a cosmos beyond our own. This single cold anomaly forces us to confront the limits of our knowledge. It demonstrates that the most subtle temperature variations are not just data points, they are profound cosmological probes. They challenge us to ask if the ultimate tools for understanding such cosmic chills are not just telescopes peering outward, but the ultra-cold atoms we are learning to control right here at home. These cosmic cold spots challenge us with puzzles on the grandest of scales, but the most profound answers may be found in the smallest of places. Inside laboratories, scientists are constructing miniature universes to see these cosmic forces in action. They are using clouds of ultracold atoms as cosmic simulators, creating tabletop models of the most extreme environments in existence. At institutions like JILA, researchers do not just cool atoms, they choreograph them. By precisely tuning magnetic fields and lasers, they can make a cloud of cold atoms behave like the fabric of spacetime itself. The atoms, held in a trap, can be made to expand or contract in a way that mathematically mimics the expansion of our entire cosmos. In this analogy, the temperature of the atomic cloud is the master control. Lowering the temperature triggers phase transitions, moments when the collective behavior of the atoms shifts dramatically, just as the early universe underwent violent phase transitions as it cooled from its initial hot, dense state. One of the most stunning applications of this technique is the simulation of Hawking radiation. According to Stephen Hawking's theory, black holes are not completely black. Intense gravitational forces at the event horizon should spontaneously create pairs of particles, with one falling in and the other escaping as a faint glow. We cannot get close to a real black hole to test this, but we can build an analog. Researchers create a sonic horizon in a flowing Bose-Einstein condensate. Where the fluid flows faster than the speed of sound, nothing, not even a ripple, can travel back upstream. This creates an effective point of no return, just like a black hole's event horizon. Incredibly, experiments have detected the spontaneous creation of phonon pairs, quantum sound waves that mimic the particle pairs Hawking predicted. One particle of the pair is trapped behind the sonic horizon while the other escapes, producing a measurable signal. This does not prove Hawking radiation exists for real black holes, but it shows the underlying quantum process is sound. It validates that our most radical ideas about the edge of reality are grounded in real physics. Physicist Emanuel Bloch takes this further with optical lattices, intricate webs of laser light that hold atoms in perfect crystalline arrays. By adjusting these lasers, his team can make the lattice expand, forcing the atoms to behave as if they are living in an exponentially stretching universe. They can watch quantum fields evolve and even simulate cosmic defects known as cosmic strings, which are theoretical cracks in spacetime. These lab-made cosmos are more than just clever demonstrations. They suggest that the behavior of the last cold atoms, held in their magnetic and optical traps, might directly mirror the fundamental physics at the edge of everything, from the birth of the universe to the evaporation of black holes. By mastering the deepest cold, we are not just observing the cosmos from a distance. We are learning to rebuild it piece by piece, atom by atom, bringing the most distant frontiers of quantum gravity within our reach. The quest to unite Einstein's graceful cosmos with the fizzing quantum world represents the final great problem in physics. For a century, general relativity and quantum mechanics have existed in separate realms, one governing the immense dance of galaxies, the other ruling the chaotic subatomic frenzy. Yet at the edge of a black hole or the moment of the Big Bang, these two theories collide and our understanding of reality breaks down. The bridge between them is a theory of quantum gravity, and the path to building it may be paved with cold. In the profound chill near absolute zero, the frantic jitter of heat vanishes, allowing the subtle whispers of quantum mechanics to roar. It is here, in this frozen quiet, that the fabric of spacetime itself might reveal its deepest secrets. Theorists like Carlo Rovelli propose that space is not a smooth continuum, but a tapestry woven from tiny, discrete loops. This is the heart of loop quantum gravity, a framework where the familiar dimensions of space and time emerge from a vast network of interconnected quantum threads. The problem is that these threads are unimaginably small, existing at the Planck scale, a realm far beyond the direct reach of any particle accelerator. But we may not need to smash particles together to see this granular structure. We might simply need to cool them down. In an ultra-cold cloud of atoms, these fundamental loops of spacetime could potentially imprint their presence on how the atoms behave, subtly altering their quantum states in ways we are just learning to detect. One of the most promising tools for this search is atom interferometry. Imagine taking a single atom and using laser pulses to split its quantum wave function, sending it along two separate paths before recombining it. The resulting interference pattern is exquisitely sensitive to any tiny changes along those paths, including minuscule ripples in gravity. By performing these experiments with atoms cooled to a near standstill, we eliminate the blurring effect of thermal motion. transforming the apparatus into a hypersensitive gravitational antenna. Projects like the International Cold Atom Experiment, or ICE, plan to do this in the quiet of space. By measuring how clouds of ultra-cold atoms fall in a vacuum, ICE could test the equivalence principle, the cornerstone of general relativity, which states that all objects fall at the same rate with a precision never before achieved. Any deviation, no matter how tiny, would send shockwaves through physics, hinting at the quantum nature of gravity itself. This is the search for the graviton, the hypothetical quantum particle that carries the gravitational force. In the calm of an ultra-cold lab, the faintest whisper of a graviton could, in theory, nudge an atom in a detectable way. These experiments are hunting for the space-time foam, a concept suggesting that at the tiniest scales, the vacuum of space bubbles and churns like a quantum sea. As we master the coldest temperatures, we are not just cooling atoms. We are calming this quantum foam, stilling its violent churn just enough to see the individual grains of reality beneath. This chilling frontier suggests that temperature itself defines the boundary where gravity and quantum physics finally meet, a convergence that may force us to rewrite our cosmic story from its very first page. The fabric of reality might be a grand illusion, a cosmic mirage projected from a simpler dimension. This is the heart of the holographic principle, a revolutionary idea born from the thermodynamics of black holes. It suggests that our universe, with all its rich three-dimensional depth, could be encoded on a distant two-dimensional surface, much like the information on a credit card hologram creates the appearance of a three-dimensional image. The mathematical foundation for this was laid by physicist Juan Maldacena with his AD/CFT correspondence. This is a duality, a powerful equivalence showing that a theory of quantum fields living on a boundary without any gravity at all can perfectly describe a universe with gravity in its interior. In this breathtaking framework, temperature is the universal translator. It connects the heat and entropy on the flat boundary to the warped gravitational physics of the bulk universe. Think of a black hole, the ultimate cosmic paradox. Stephen Hawking calculated that a black hole is not completely black. It possesses a temperature, a faint heat proportional to its surface gravity. This heat leads to Hawking radiation, a slow evaporation where the black hole leaks energy and information back into the cosmos. The holographic principle resolves what happens to the information swallowed by the black hole. It is not lost inside the singularity. Instead, it is smeared and stored across the black hole's two-dimensional event horizon, its surface area acting as the maximum hard drive for cosmic data. The amount of information it can hold is directly linked to its entropy, a measure of disorder that is intrinsically tied to its temperature. A hotter black hole with higher entropy has a larger information storage capacity on its boundary. Now, scientists are testing these mind-bending ideas not with giant telescopes, but with the last cold atoms in laboratories. By creating carefully controlled Bose-Einstein condensates, they can engineer quantum systems that mimic the mathematics of holographic duality. They can adjust the temperature of their atomic cloud and observe how information propagates and scrambles across it, simulating how data might be encoded on a cosmic horizon. The profound chill of these experiments is essential. It suppresses thermal noise, allowing the subtle quantum signatures of holographic information processing to emerge from the background. This suggests that the very coldness of a system might define its capacity to encode a richer, more complex reality. If the holographic principle is true, then the edge of everything we perceive is not a physical barrier, but a thermal one, a surface defined by its temperature and information density. This leads to an even more startling possibility that the accelerating expansion of the cosmos, driven by dark energy, might itself be a thermal phenomenon written on the ultimate cold boundary of our holographic universe. The accelerating expansion of the universe is driven by a force that defies gravity, a mysterious pressure known as dark energy. As our cosmos cools and stretches into a vast, thinning void, this enigmatic influence grows ever more dominant, overwhelming the collective pull of all matter. Nobel laureate Dr. Adam Rees and his team made this startling discovery by observing distant supernova, the explosive deaths of white dwarf stars. They found that these cosmic beacons were fainter than expected, meaning the universe is not just expanding, but its expansion is speeding up. The engine for this acceleration seems to be intrinsically linked to the growing coldness of space itself. One of the leading explanations is the cosmological constant, an idea first proposed by Einstein. This model equates dark energy with the vacuum energy of empty space, a fundamental energy whose repulsive force becomes noticeable only when the universe grows large, sparse, and cold. In this view, the chill of the cosmic voids is not a passive condition. It is an active participant in the cosmos's ultimate fate. Could it be that cold regions of space actually generate a form of repulsive gravity? Some theories suggest that in the immense matter-starved voids between galaxies, the influence of dark energy creates a subtle, negative pressure that pushes space-time apart. This effect might be detectable by studying the fossilized ripples of the early universe, patterns known as baryon acoustic oscillations. These are the imprints of ancient sound waves that traveled through the primordial plasma, leaving a statistically regular spacing between galaxies that persists to this day. By mapping the distribution of galaxies across these cold voids, astronomers can measure how dark energy has stretched this cosmic ruler over time, testing whether its strength truly varies with the temperature and density of the region. This profound connection between cold and cosmic repulsion brings the quest back to our laboratories. If dark energy's properties are tied to the energy of the vacuum, and that vacuum behaves differently at ultra-low temperatures, then the last cold atoms we create become vital experimental tools. By studying how these atoms interact in a near-perfect vacuum chilled to almost absolute zero, we can search for minute shifts in their behavior. These shifts could help calibrate the equation of state for dark energy, a parameter that describes whether its strength is constant or changes over time. This is not just about understanding an abstract force, it is about forecasting the ultimate destiny of everything. The relentless push of dark energy, amplified by the growing cold, points toward a final state known as the heat death of the universe. In this distant future, the cosmos will have expanded so much that the last stars will have long since burned out, and all matter will be scattered across an infinite, ever-cooling void. The universe would reach a state of maximum entropy, a final, uniform temperature just a fraction of a degree above absolute zero, where no energy can flow and no change can occur. It is the last cold atoms adrift in that final darkness that would bear witness to the end of time. The final state of the cosmos will be one of profound and permanent cold. This is the heat death of the universe, a finale defined not by fire or ice, but by a slow, irreversible fade into maximum entropy. Over trillions upon trillions of years, the last stars will exhaust their nuclear fuel and wink out of existence. Galaxies will drift apart into an ever-expanding darkness, their stellar cinders cooling toward the background temperature of space. Even the mightiest black holes, having consumed all they can, will slowly leak their mass away through Hawking radiation, eventually vanishing in a final, faint puff of energy. What remains is a universe stretched impossibly thin, a near-perfect vacuum where the temperature is almost uniform, just a fraction of a degree above absolute zero. There are no hot spots left, no cold spots, just a vast, featureless sea of sameness. Physicist Sean Carroll describes this as the ultimate equilibrium, a state where no energy can flow because there is nowhere for it to go. No work can be performed, no processes can run, and the cosmic clock effectively stops. Think of a hot cup of coffee left on a counter. It does not explode, it simply cools, its heat dissipating into the room until it reaches the same temperature as its surroundings. At that point, the coffee and the room are in equilibrium, and the journey is over. The heat death is this same process writ across the entire cosmos, a cup of coffee cooling to room temperature on a scale of unimaginable vastness and time. In this frozen, dark future, the last cold atoms would be those drifting in absolute isolation, their motion so slow that eons pass between the most minuscule of interactions. They are the final relics of a once vibrant universe, bearing witness to a stillness so complete that information itself may be lost, its patterns erased by the relentless drive toward disorder. This chilling prospect forces a profound question about the nature of existence. Could any form of life or consciousness persist in such a state, where change is impossible and time has lost all meaning? The very definition of life relies on energy gradients, on the ability to do work and process information. In the heat death, those prerequisites vanish. The ultimate edge of everything may not be a spatial boundary, but a thermal one, a final temperature that marks the end of possibility and the quiet triumph of entropy over all structure and story. The profound silence of the cosmos might be a direct result of its deep chill. We have scanned the skies for decades, listening for any signal, any sign that we are not alone, and yet the universe answers only with quiet. This is the heart of the Fermi paradox, the puzzling contradiction between the high probability of alien civilizations and our complete lack of evidence for them. The solution may not lie in distant stars, but in the pervasive cold that fills the space between them. Warmth is the currency of life, and the universe is a place of immense financial inequality. Astronomer Frank Drake captured this in his famous equation, which includes the critical factor of a star's habitable zone. This is the narrow orbital band where temperatures are just right for liquid water to exist, a region defined entirely by heat. Venture too close to a star and the heat sterilizes everything. Stray too far and the cold locks all chemistry in a frozen prison. The vast majority of real estate in any solar system, and indeed in the galaxy, is a lethal deep freeze. Consider our own cosmic backyard. The polar ice caps of Mars are a frozen desert where any potential microbial life would be locked in suspended animation, if it exists at all. The subsurface ocean of Jupiter's moon, Europa, may hold liquid water, but it is buried under a shell of ice kilometers thick, its chemistry playing out in perpetual darkness and cold, a challenging cradle for any complex biology. The very atoms that make up life require a certain energy, a warmth, to interact, bond, and build the intricate structures of DNA and proteins. In the near absolute zero of interstellar space, chemical reactions slow to a near standstill. The building blocks of life simply cannot assemble in the dark, cold voids that comprise most of the universe. This cosmic refrigeration could be the ultimate great filter. Perhaps intelligent life does spark into existence, but it remains trapped on its warm, home-world island, surrounded by an ocean of cold too vast and deadly to cross. The energy required to traverse these frigid gulfs, to sustain life for generations in the void, may be too great for any civilization to overcome. The silence we hear may not be a sign of absence, but a testament to the cold, hard reality that temperature erects a biological barrier as formidable as any physical one. It defines not only the edge of stars and galaxies, but the very boundary of life itself, pushing our search for connection toward the rare and precious pockets of warmth. Our search for cosmic neighbors is fundamentally a hunt for heat. Astronomers define a star's habitable zone as the narrow orbital region where temperatures are just right for liquid water to exist on a planet's surface. This concept, often called the Goldilocks zone, is not too hot and not too cold, but it is exceptionally rare in the vast, chilly expanse of a typical solar system. Pioneering scientists like Sarah Seeger have dedicated their careers to finding these warm specks in the darkness. Using data from telescopes like Kepler, they analyze the faint dimming of a star's light as a planet transits across it. This dip in brightness reveals the planet's size, but the true magic happens when they study the starlight filtering through the planet's atmosphere. By breaking this light into a spectrum, they can detect the chemical fingerprints of water vapor, methane, and other gases, allowing them to infer the world's surface temperature and assess its potential for life. The type of star is crucial. A small, cool red dwarf like Proxima Centauri has a habitable zone that is incredibly close in. Its planet, Proxima Centauri b, orbits 20 times nearer to its star than Mercury does to our Sun. This proximity creates an entirely different set of rules. The gravitational pull is so strong that the planet is likely tidally locked, with one hemisphere in perpetual daylight and the other in endless night. The result is a world of extreme temperature gradients. The day side might be warm enough for liquid water, while the night side is frozen solid. A stark, cold landscape where any atmosphere could condense into ice on the surface. The TRAPPIST-1 system presents a similar puzzle, with multiple Earth-sized worlds huddled around their dim star. Their atmospheres, if they have any, would be the ultimate arbiter of their fate. A thick, insulating blanket of greenhouse gases could distribute heat around the planet, warming the frigid side. A thin or non-existent atmosphere, however, would surrender to the cold, leaving the world a barren rock. This relentless search for warmth underscores a profound truth. Temperature is the gatekeeper of biology. The complex chemistry of life requires the energetic dance of atoms and molecules, a dance that simply cannot begin in the deep freeze of interstellar space. The last cold atoms, adrift in the void or held in our labs, represent the absolute antithesis of a living world. They exist in a state of minimal energy and motion, a realm devoid of the biological potential that defines our own warm, wet planet. To even detect these cosmic cold spots and the faint warmth of distant exoplanets, we have been forced to create a new generation of sensors, technologies born from our very mastery of the cold. High above the Earth, floating in the pristine quiet of the International Space Station, a refrigerator the size of a small suitcase is quietly rewriting the rules of quantum physics. This is the Cold Atom Lab, a facility that leverages the most underappreciated tool in science, microgravity. On our planet, the delicate quantum states of ultra-cold atoms are constantly pulled down by gravity, limiting observation times to mere fractions of a second before the cloud simply falls out of the apparatus. But in orbit, freed from this relentless tug, these fragile states can persist for over 10 seconds, an eternity in the quantum world. NASA doctor Kamal Audriri explains that this extended lifetime is transformative. It allows researchers to create Bose-Einstein condensates and watch them evolve with a clarity impossible on Earth. They can study the atoms as they slowly expand, observing their wave-like properties as they ripple and interfere with each other in a delicate, extended ballet. This is not just about watching atoms get colder, it is about giving them the time and space to reveal their deepest secrets. One of the lab's key investigations involves atom interferometry. Scientists use laser pulses to split a single atom's quantum wave function, sending it along two separate paths before recombining it. The resulting interference pattern is a hypersensitive probe for measuring tiny forces, including the faint ripples of gravitational waves. The stability afforded by the space environment makes these measurements extraordinarily precise, with potential applications for next-generation navigation systems that could far surpass today's GPS. The Cold Atom Lab also meticulously studies wave packet dynamics, observing how a cloud of atoms spreads out over time. This fundamental research mirrors the behavior of matter in the vast, cold voids of space, where isolated atoms drift for eons. The data gathered in this orbital outpost provides a crucial bridge, connecting the controlled chill of our labs to the natural deep freeze of the cosmos. By mastering these quantum behaviors in the void of orbit, we are not just doing physics. We are calibrating the ultimate thermometer for the universe, one that can measure the most subtle forces shaping reality itself. The next generation of observatories is already reaching for these cosmic chills. Perched 1 million miles from Earth, the James Webb Space Telescope peers into the hearts of cold, dark gas clouds, the very nurseries where stars are born. Its infrared eyes are uniquely suited to detect the faint heat signatures of dust and molecules chilled to just a few tens of degrees above absolute zero. By mapping the temperature and density of these frigid nurseries, Webb can watch the gravitational collapse that ignites new suns, revealing how planetary systems like our own first coalesce from the cold. But the quest goes even deeper. The European Space Agency's planned LISA mission, a space-based gravitational wave observatory, will operate in the profound quiet of the interplanetary void. Its trio of spacecraft, flying in a perfect triangle millions of kilometers apart, will detect ripples in spacetime from the mergers of supermassive black holes. To achieve the necessary sensitivity, its core components must be isolated from all thermal noise, operating in an environment of extreme cold. This allows LISA to listen for the low-frequency hum of the cosmos, a gravitational soundtrack that is utterly silent to Earth-based detectors. Further out, in the frozen fringes of our own solar system, lie targets for future probes. The Kuiper Belt and the distant Oort cloud are realms of perpetual twilight, where temperatures hover near a mere 30 Kelvin. These icy bodies are time capsules, preserving the pristine, cold material from which the planets formed. Proposed missions would send spacecraft equipped with cryogenic spectrometers to these distant frontiers. These instruments, themselves cooled to near absolute zero to maximize sensitivity, would analyze the chemical composition of this ancient ice. Each frozen worldlet is a ledger, recording the temperature and conditions of the early solar system. Even our most veteran travelers are contributing to this map. The Voyager probes, now in interstellar space, are measuring the density and temperature of the cold plasma that fills the void between the stars. This tenuous gas is the baseline medium of our galactic neighborhood, and understanding its properties is crucial for modeling how our solar system moves through the cosmos. These missions, from the grand observatories to the intrepid interstellar scouts, share a common goal. They are building a detailed thermal map of the universe, from the coldest voids to the frozen remnants of our own cosmic backyard. This data does more than satisfy curiosity. It feeds directly into our theoretical models, helping us simulate the behavior of dark matter halos and test ideas about the quantum vacuum. By physically touching these cold frontiers, we are grounding our most profound theories in the hard, measurable reality of temperature, bringing the last cold atoms of deep space within our understanding. Einstein's theory of relativity tells us that gravity does more than bend space, it warps time itself. A clock ticks slower in the powerful grip of a massive object than it does out in the empty void. We experience a tiny version of this every day. The atomic clocks on GPS satellites in orbit, farther from Earth's mass, run just a fraction of a second faster than identical clocks on the ground. If we didn't correct for this, your phone's navigation would fail within minutes. But to measure these subtle effects, to truly probe the fabric of space-time, we need clocks of almost unimaginable precision. The key to building them lies in achieving the deepest cold. In laboratories like that of physicist Jun Yi, the world's most accurate atomic clocks operate at temperatures just a whisper above absolute zero. Why does cold matter so much for telling time? The answer lies in the atoms themselves. In a warm gas, atoms jitter and collide in a chaotic dance. This thermal noise blurs the very vibrations we use to measure the passage of time, like trying to listen for a perfect musical note in a roaring hurricane. But when we cool atoms to near stillness, that chaos vanishes. The atoms enter a state of exquisite order, with their quantum waves synchronizing for extended periods. This is known as having a long coherence time. It allows the atoms to act as a pristine pendulum, ticking with unwavering stability for much longer. This incredible precision opens a new window onto relativity. These cold atom clocks are so sensitive they can detect the minute time dilation caused by a mere centimeter change in elevation. On a tabletop, one clock will tick imperceptibly slower than another placed just slightly higher, because it feels Earth's gravity a tiny bit more strongly. Now extend this thought to the edge of a black hole. There, gravity is so intense that time slows to a crawl relative to the rest of the universe. A cold atom clock, with its long coherence and flawless ticks, would measure this dramatic slowing with perfect clarity. From its perspective, time would pass normally, but to a distant observer, its every tick would be stretched into an eon. This reveals a profound connection. The cold that gives the clock its precision is the same condition that magnifies time's malleability. Temperature is not just a property of matter, it is woven into the very continuum of space-time. It dictates how clearly we can observe time's flow and how extreme gravity can stretch a single moment into eternity. This temporal chill suggests that at the ultimate boundary of reality, where gravity and quantum mechanics meet, we might not find a place but a state of being, a frozen moment where time itself has finally and completely stopped. The profound cold we have been exploring does more than challenge physics. It forces us to confront the very nature of reality. Our entire cosmic story is framed by temperature, from the searing hot birth of the Big Bang to the final, frozen equilibrium of heat-death. Philosopher Tim Maudlin suggests that physical properties like temperature are not just readings on a scale. They actively shape the structure of our perception and the limits of what we can know. The universe can be seen as a single, cooling ember, its initial fire slowly dissipating into an irreversible cold. In this grand thermal narrative, where does that leave us? The very fact that we exist to ask these questions is a direct result of a specific, fleeting temperature gradient. Our consciousness, our ability to perceive time and change, relies entirely on energy flows that will one day cease. A perfectly cold, uniform universe would be a cosmos without story, without memory, and without observers. It raises a haunting possibility that the edge of everything is not a wall in space, but a boundary of experience defined by heat. Yet within this deep chill lies a tantalizing paradox tied to information. The laws of quantum mechanics suggest that information is never truly destroyed. In the context of black holes, this created a famous paradox where information swallowed by the singularity seemed to vanish, violating quantum principles. The resolution, hinted at through holographic principles, is that the information is not lost but preserved on the event horizon. This idea of data immortality finds a curious echo in our ultra-cold labs. The quantum states of the last cold atoms held in their magnetic traps can encode information with incredible stability, protected from the disruptive noise of heat. If the final state of the universe is a sea of such cold, near-motionless atoms, could the information of all that ever was, every star and every thought, be frozen into a permanent, if inaccessible, record? It is a cosmic form of archival, where the universe itself becomes a vast, cold hard drive storing its own history. This philosophical chill invites a humbling reflection. We are temporary creatures of a temperate era, living in a narrow window between fire and ice. Our entire reality is possible only because we inhabit a warm speck in an overwhelmingly cold cosmos. The practical applications of cold atom research, from quantum computers to hyper-precise sensors, are not just technological triumphs. They are our way of learning to read this cosmic ledger, to understand the rules of a reality whose ultimate boundaries are not made of space but of temperature. The same physics that chills atoms to a near standstill is now powering a technological revolution. Inside sleek, cylindrical refrigerators in research labs from IBM to Google, quantum bits or qubits are held at temperatures colder than the void of deep space. These qubits are the heart of quantum computers, and their fragile quantum states can only be protected from disruptive noise in an environment of profound cold. At mere thousandths of a degree above absolute zero, these systems can perform calculations in minutes that would take today's most powerful supercomputers thousands of years. This is the race for quantum supremacy, and it is fundamentally a race to master the cold, but the impact extends far beyond computing. In hospitals, the principles of cold atom research are enhancing magnetic resonance imaging, or MRI. New generations of ultra-sensitive magnetometers, inspired by the same atomic interferometry used to probe gravity, can now map the human brain's magnetic fields with unprecedented clarity, offering new windows into neurological conditions without any invasive procedures. The navigational systems of the future are being built on this foundation as well. Where ships and aircraft once relied on spinning gyroscopes, they may soon navigate by atom interferometers. These devices use the wave nature of ultra-cold atoms to measure rotations and accelerations with a precision that never drifts, creating an inertial guidance system that could guide a submarine beneath the polar ice without any contact with GPS satellites. Perhaps one of the most transformative applications lies in the quest for room temperature superconductors. By studying how electrons pair up and flow without resistance in the simplified environment of ultra-cold atomic gases, scientists are decoding the secrets of superconductivity. A practical, high-temperature superconductor would revolutionize our world, enabling lossless electrical grids that waste no power, maglev trains that glide effortlessly, and medical imaging machines that are far more powerful and affordable. These are not distant dreams, they are active engineering challenges being solved with insights forged in the cold. This profound link between the deepest cold and cutting-edge technology suggests that our ability to control temperature is directly shaping the next chapter of human progress. It forces us to look closer to home, to the delicate thermal balances that sustain our own world. Our own planet holds frozen laboratories that mirror the cosmic chill. Here on Earth, the polar regions are not just barren landscapes, they are active, breathing records of how extreme cold shapes existence. In the Arctic, scientists like Dr. Katie Walter Anthony study permafrost, ground that has remained frozen for thousands of years. As this permafrost thaws, it releases ancient methane, a potent greenhouse gas, creating a feedback loop that accelerates climate change. These icy layers are a living diary of our planet's past atmosphere, and their changing state is a stark warning about the delicate thermal balance that sustains life. The glaciers that carve through mountains and the vast ice sheets of Greenland and Antarctica are not static. They flow, they fracture, and they preserve history in their frozen depths, acting as direct analogues for the icy crusts of moons like Europa or Enceladus. To understand how life might persist on a frozen world, researchers travel to the McMurdo Dry Valleys of Antarctica, one of the coldest and driest deserts on Earth. This terrain is the closest we get to the surface of Mars without leaving the planet. In this hyper-arid, frigid environment, life clings to existence in the most minimal ways. Microbes survive within rocks, and tiny, almost indestructible creatures called tardigrades can enter a state of suspended animation called cryptobiosis. In this frozen sleep, they dehydrate their bodies and shut down their metabolism, able to withstand the vacuum of space and temperatures near absolute zero for years, only to reanimate when conditions improve. The resilience of these earthly extremophiles forces a profound shift in our perspective on life itself. It suggests that biology is not a fluke of comfortable warmth, but a process that can persist, paused at the very edge of cold. The same temperature gradients that create a habitable zone around a star also create microhabitats within a single grain of ice. This earthly research directly informs the search for life elsewhere. When we design a probe to drill through the icy shell of Europa, we are applying lessons learned from studying subglacial lakes in Antarctica. When we ponder the chemistry of a cold, dark ocean, we look to the isolated, brine-filled veins within Arctic sea ice. Our planet's cold frontiers teach us that temperature is a universal architect, sculpting worlds from the microscopic to the galactic. The slow creep of a glacier and the relentless expansion of the cosmos are both stories written in the language of heat and its absence. By learning to read the cold on Earth, we are deciphering the same fundamental principles that govern the last cold atoms at the edge of everything. These vast temperature scales, from the quantum to the cosmic, are not isolated realms but deeply intertwined threads in a single tapestry. At the quantum scale, an ultimate upper limit exists: the Planck temperature, a staggering 1.4 times 10 to the 32 Kelvin. At this inconceivable heat, the very forces of nature would unify, and our current laws of physics break down completely. This fiery ceiling and the frozen floor of absolute zero create the fundamental frame within which all physical processes in our universe must operate. Cosmologist Dr. Brian Greene points out that this thermal hierarchy defines the operational realms of reality. The rules that govern a superheated plasma are utterly different from those that rule a Bose-Einstein condensate, yet they are two expressions of the same underlying principles, separated only by the amount of energy present. A stunning example of this convergence is the neutron star. Its surface, forged in a supernova explosion, can blaze at over 1,000,000 Kelvin, emitting intense X-rays that we can detect across the galaxy. Yet dive deep into its core and you may find a form of matter that is profoundly cold. This is degenerate matter, where neutrons are packed so densely by immense gravity that they are stripped of their thermal energy. Their behavior is governed not by heat but by quantum pressure, a cold, mathematical order imposed by the Pauli exclusion principle. This means a single object can harbor both stellar fire and a deep quantum chill simultaneously. The last cold atoms we create in our laboratories exist at the precise frontier where these scales meet. They are not just cold, they are the point where the frenetic energy of the quantum world is quieted just enough for us to observe its most delicate features. Features that might also be present in the cold heart of a neutron star or the diffuse halo of dark matter. This unified thermal view prompts a final, humbling reflection. Our entire understanding of the cosmos, from the birth of particles to the fate of galaxies, is written in the language of temperature. As we stand at this threshold, what ultimate secrets might these cold atoms reveal about the universe's first moments or its final state? The greatest mysteries of cold are still waiting to be unlocked. Even the concept of absolute zero is no longer an absolute limit. In laboratories like that of Dr. Marcus Grainer, scientists are creating systems with temperatures defined as below absolute zero, a realm of negative Kelvin. This does not mean the atoms are colder than absolute zero, which is impossible. Instead, it signifies an inverted energy distribution. Think of it like a mountain. In a normal, positive temperature system, most atoms are in the valley with a few energetic ones on the slopes. A negative Kelvin state inverts the mountain, placing most atoms at the peak, a condition of maximum energy but described with a negative temperature scale. Achieving this requires exquisite control, using laser traps to create energy landscapes where atoms with the highest energy are actually the most stable. In this bizarre realm, matter behaves in ways that defy intuition. Atomic clouds might resist collapsing under their own gravity, a property that could offer clues to the repulsive force of dark energy. Could the vacuum energy that drives the universe apart share a mathematical kinship with these inverted systems? This is one of the profound questions now being tested. The frontier also extends to the very shape of reality. Could we use these ultra-cold atoms to detect evidence for extra dimensions? Some theories suggest that if tiny, compact dimensions exist, they would subtly alter how atoms interact at these incredibly low energies. A minute shift in the vibration of a cold atom lattice could be the signal that our universe has a hidden geometry. The most tantalizing application lies in the hunt for dark matter. If the elusive action particle exists, it would interact so weakly with normal matter that its signal is drowned out by thermal noise. But in a sensor built from the last cold atoms, where that noise is silenced, the faint whisper of an action passing through might finally be detected. These unresolved challenges reveal that our journey to the edge of cold is far from over. The last cold atoms are not a destination, but a gateway. They are our most sensitive instruments for probing the universe's greatest mysteries, from the nature of the quantum vacuum to the composition of the cosmos. This ongoing quest confirms that temperature is more than a measurement. It is the fundamental lens through which we will continue to define and explore the very edge of everything. Our journey from the cosmic deep freeze of the Boomerang Nebula to the quantum calm of our laboratories reveals a stunning truth. Temperature is far more than a number on a scale. It is the universe's master sculptor. It carves the quantum behavior of a single atom and dictates the ultimate fate of entire galaxies, defining the very edge of everything we can know. The last cold atoms we study are not merely a scientific curiosity. They are a profound gateway, a lens through which we can bring the universe's grandest mysteries into sharp focus. In their near-perfect stillness, we find clues to the invisible architecture of dark matter, the elusive union of gravity and quantum mechanics, and the very nature of reality woven from the fabric of information. This exploration invites you to step outside on a clear night and gaze into the darkness between the stars. Those vast, cold voids are not empty. They are vibrant with potential, holding the keys to existence itself, written in the language of cold. If this journey into the chill at the edge of everything sparked your curiosity, subscribe for more deep dives into the mysteries of space. Share your thoughts in the comments below and tell us how you believe temperature defines the boundaries of our reality. Remember, in the immense quiet cold of the cosmos, the smallest atoms may very well hold the very biggest answers.